In this presentation, we are going to learn about circumpolar bodies. The literal meaning of the word circumpolar is making circles around the pole. Now, fundamentally speaking, all the celestial bodies, they move in circles around the pole. All the celestial bodies move on their declination circles, and all these declination circles are centered at the pole only. But as far as the circumpolar term is concerned, we call those bodies as circumpolar whose circular motion is visible to us. The complete circular motion around the pole is visible to us. In other words, a body is said to be circumpolar if the body is always above the rational horizon of the observer. That is, the body should not set. During the full day, the body should not set. These type of bodies are called as circumpolar bodies. They remain above the horizon of the observer, and you are able to visualize or you are able to see them at any time of the day for full 24 hours. Now let's try to understand when does a body become circumpolar, or what are the conditions which lead to a body becoming circumpolar. This can be easily understood from a rational horizon diagram. Now let's assume that our observer is in northerly latitude in the north hemisphere. You can assume latitude close to 40 degrees north or so. And let's make a rational horizon diagram for the observer. We have the rational horizon. We mark off the NESW points on the rational horizon. Then we mark the celestial meridian of the observer. We mark the prime vertical circle. Exactly at the center of this diagram is the zenith of the observer, represented by Z. Now, since the observer is in the north hemisphere, the latitude is north, equinoctial will be passing south of the observer. So from point Z, if we go down south equal to our latitude, now that gives us the point from where the equinoctial will be passing. It is represented as point Q in the rational horizon diagram. We are aware that equinoctial always passes from west and east points. So now we know that the equinoctial will pass from W, Q, and E. And we can now show the equinoctial in our diagram. We have the equinoctial here. Now, once the equinoctial is there in the diagram, we can also show the pole. In this case, the observer is in north hemisphere, so the north celestial pole will be the elevated pole or the visible pole, and it will be 90 degree away from the equinoctial. So 90 degree away or 90 degree north of the Q point, this is where the pole would lie. So let's mark this point as P, representing the north celestial pole. Now in this diagram, let's assume some celestial bodies of different declinations, and let us see whether they become circumpolar for this particular observer or not. Let us first assume a body with a declination opposite to the latitude. The latitude in this case is north. So let's assume a body having a southerly declination. Now in this diagram, we are aware that this N point is on the horizon. The P point represents the pole, and this N to P, what is highlighted by this yellow line, is called as the elevation of the pole or the altitude of the pole. And this is always equal to the latitude of the observer. We can easily understand it from the diagram. Now, the N point is 90 degree away from the Z point, from the zenith. because every point on the rational horizon is 90 degree away from the zenith of the observer. Similarly, the P point, which represents the pole, is 90 degree away from Q point, which is the equinoctial. So P to Q is 90 degrees, that is pole to equinoctial. N to Z is 90 degrees, that is rational horizon to zenith. So therefore, what is the arc ZQ? It will be exactly the same as arc NP. ZQ was the latitude of the observer, so NP, which is the altitude of the pole or elevation of the pole, will also be equal to the latitude of the observer. So let's now assume some celestial body. As I told you, first let's assume a body having a southerly declination. So we have a star here. You can see it is south of the equinoctial, having a southerly declination. Let's try to show the path of this star, the path on which this moves, that is the declination circle of this particular star. All the declination circles are parallel to the equinoctial. So the declination circle of this particular star parallel to the equinoctial would appear something like this. The declination circle shows us the path on which the body moves. Now this body is going to rise at this particular point on the horizon. You can follow the laser pointer on the screen. This is the point where the body is going to rise on the eastern horizon. After rising, it will move on its declination circle. It will cross the meridian of the observer at this particular point and then cross over to the western side, and eventually it will go and set at this particular point on the western horizon. And we can see here that this body is certainly not circumpolar, because at this particular point it is going to go below the horizon of the observer. Now you could have picked up a body of any southerly declination lying between Q and S points, and you will see that all those bodies' declination circle will hit the western horizon at some point, making that body go below the horizon. So any body with a declination opposite to the latitude will not be a circumpolar body. So this is one thing which we have seen now. Now let's assume a second celestial body with its declination of the same name as latitude of the observer and see whether it becomes circumpolar or not. So you can see in the diagram, this is the rising point of the body. A body moves in this particular direction represented by the arrow and then eventually sets at this particular point. Now let's assume a second body here. Now this star is north of the equinoctial, and the declination of the star is of the same name as the latitude of the observer. Let's try to show the declination circle of this particular star. The declination circle will pass through the body and it will be parallel to the equinoctial. So this is how the declination circle is going to appear. On this declination circle, the body will be moving in this particular direction represented by the arrow. The body will be rising at this particular point, moving in this particular direction, crossing the meridian here, and at this particular point the body is going to set. So we saw that even this particular body is not circumpolar. So it is not necessary that with lat and dec of the same name a body should certainly be circumpolar. Let's try to increase the declination a little bit now. Let's assume a third body, this particular star now. This is also having a northerly declination, but the declination is more than what we had in the previous case. Let's try to draw the declination circle of this particular star. Now declination circle will pass from the body and it will be parallel to the equinoctial. Now in this case, the declination circle is going to be like this. All the declination circles are centered at the pole. So centered at the pole, polar distance equal to px, pole and the body. if you draw a circle that gives you the declination circle of this particular star. Now the arrows show the direction in which the star will be moving on this particular circle. Now we can clearly see that the entire declination circle of this particular star is above the horizon of the observer. It touches the horizon at the north point, but never goes below the horizon. So these bodies which remain above the horizon of the observer for full 24 hours and never set are circumpolar bodies. So one thing we have seen from this diagram that it is certainly not possible to have a body circumpolar with lat and dec for opposite names. So one condition which we can pick up from this rational horizon diagram is that for a body to be circumpolar, the first condition is the latitude and declination. Latitude of the observer and declination of the body should be of the same names. Beta, any doubt up to here at any of the points?
No, sir.
Okay, all right, let's proceed ahead.
Can you please revise that slide so I can take the screenshot?
Okay, beta, just give me 1 minute. This is the one, beta.
Okay, sir.
Okay, let's proceed ahead now. We have seen that lat and dec should be of the same name for a body to be circumpolar. Now in this diagram, I have also shown the polar distance of the body. P to X, this represents the polar distance of this circumpolar star, and it is always equal to 90 minus declination. So polar distance in this case, which is 90 minus declination, is shown in the diagram. Now we can clearly see in this particular diagram that for a particular body to be circumpolar, the polar distance of the body, which represents the radius of the declination circle, should always be less than or equal to NP. If the polar distance is more than NP, then you can clearly see from the diagram that the declination circle will go beyond the horizon of the observer. It will go below the horizon of the observer, making the body not a circumpolar body. If it has to be circumpolar, the radius of this circle, that is Px, should be equal to or less than Np. If the radius is equal to Np, you will have exactly this particular condition. The circle will be touching the horizon at point N. And if the radius is less than Np, then the entire circle will be within the rational horizon of the observer. So we understand from this diagram now that for a body to be circumpolar, this condition should be met. That is, the polar distance of the body should be equal to or less than the elevation of the pole, or NP. Now, NP, or elevation of the pole, is equal to the latitude of the observer. So we now come to this relationship that Px, which is the polar distance, should be less than or equal to Np, which is the latitude. Now polar distance is equal to 90 minus declination. So this converts the relationship into 90 minus declination should be less than or equal to the latitude of the observer. Now, if I take declination to the other side, to the right-hand side, the relationship becomes latitude plus declination should be greater than or equal to 90 degrees. So this is the second condition which needs to be fulfilled for a body to become circumpolar. The first condition which we saw in the previous slide was that the latitude and declination should be of the same names. The condition which we saw in this particular diagram is latitude plus declination should be greater than or equal to 90. So these are the two conditions which needs to be met for a body to become circumpolar. Latitude and declination same names, and latitude plus declination greater than or equal to 90 degrees. So remember these two conditions for a body to become circumpolar. So beta, any doubt up to here you can share with me, beta?
No, sir.
Okay, very good. If you want, you can take a screenshot of this particular screen, and this gives you a diagram as well as the two conditions when the body becomes circumpolar. So let's proceed ahead then. We are clear about these two conditions now. Whenever any celestial body fulfills these two conditions, we know that this body should be circumpolar. Now, if I ask you, beta, one question, can the sun become circumpolar at the place where you are? Let us say you are at 30° north latitude.
No, sir.
No,
No.
sir. No.
Yeah, that's right. It can never become. And now you know the answer. Sometimes they ask you like that in your oral exams. They will simply ask you that can the sun be circumpolar here? And whatever is your answer, then they will ask you why is it that. So if you say no, they will ask you why. Then you can simply tell them that for body to be circumpolar, the lat plus dec should be greater than 90. With our latitude at 30 and sun's maximum declination at 23 and a half, it is not possible for it to be greater than 90 degrees. So anyway, let's proceed ahead now. Now going a little more deeper into the circumpolar bodies, we had this particular star, and the polar distance is less than or equal to NP in this case. And you can see the entire declination circle of the star is within the rational horizon of the observer. So this is a circumpolar star. Now, the direction of this, the motion of the star is represented by these two arrows. Now, in this particular diagram, we can see that the star comes north of the observer at two instances. At point A here, it will be north of the observer. The bearing of the star would be 0, 0, 0. And again, when it reaches or crosses the meridian at point B, it will be again north of the observer with a bearing 0, 0, 0. Now, this is only possible in case of a circumpolar body. For a normal body which is not circumpolar, it will come north or south of you, or in other words, you can say it will come on your meridian only once in a day. But a circumpolar body will be north or south of you twice in a day, roughly after an interval of 12 hours. it will be south or north of the observer 2 times in a day. Now, both of these instances are called as meridian passages. One of them is the meridian passage on the observer meridian. If you look carefully in the diagram, P is the pole and P, Z, Q, S is the observer's meridian, and you can see that at point B, the body crosses the meridian of the observer. Now at the second instant, that is at point A, it is crossing the inferior meridian of the observer, or the opposite meridian of the observer. You see, when you go on other side of the pole, this represents your inferior meridian, reciprocal meridian. So at point A, the body crosses the inferior meridian of the observer. At point B, it crosses the meridian or the observer's meridian. Now point A is known as meridian passage on the inferior meridian. You can call it the meridian passage of the body on the inferior meridian, or you can also call it meridian passage below the pole. Now, why do we call it meridian passage below the pole? That also can be seen easily from this diagram. We know N to P is the elevation of the pole or the altitude of the pole. So N to P represents the elevation or altitude of the pole. N to A represents the elevation or altitude of the body at the time of meridian passage on the inferior meridian. And we can clearly see that the altitude of the body is lesser than the altitude of the pole. That is why at this particular instant, that is at point A, the meridian passage of the body occurs below the pole. Now this is, for this particular reason, this is also called as lower meridian passage or lower marpass. At the same time, the point B which you see is known as the meridian passage on the observer's meridian. Point B represents the meridian passage on the observer's meridian. It is also called as meridian passage above the pole, because you can see at this point the altitude of the body is represented by NB, November Bravo. The altitude of the pole is NP, November Papa, and the altitude of the pole is less than the altitude of the body. The body is at a higher altitude at point B. So that is why it is called as meridian passage above the pole. And it is also known as upper marpass or upper meridian passage, because at point B the body is above the pole. It is at a upper location than the pole. So upper marpass and the lower marpass. Upper marpass or meridian passage above the pole is on the observer's meridian. Lower marpass or meridian passage below the pole is on the observer's inferior meridian. Now, if you remember, when you look for the meridian passage time of the moon in the almanac, there are 2 times which are given, one under upper and other under lower. This upper and lower basically means the meridian passage of the moon on the observer's meridian, that is for upper, and for lower, it is the meridian passage of the moon on the observer's inferior meridian.
सर
बोलो बेटा.
सर एक डाउट था सर, ये अराउंड 70 डिग्री नॉर्थ एंड अबव सन इज आल्सो ए circumpolar body.
That's right, beta. It can be circumpolar.
And sir, if it is circumpolar, then in the nautical almanac only for the this moon is given this 2 timings, lower and upper. Why not for the sun?
Okay, very good, beta. Anybody can think about this and answer?